So we've looked at how to do a confidence interval for a proportion. That was unit 7. That was the first part of unit 7. Last class, on Monday, we looked at how to do a confidence interval for a mean. And then in unit 7, we looked how to do a hypothesis test for one proportion. And now we're going to look at how to do a hypothesis test for one mean, which is essentially the same, except again, remember, and you got to know this whenever you see questions, whether you're dealing with a mean or a proportion, because it's slightly different what we do, and the notation is slightly different. I mean, with proportions, we're trying to find a confidence interval or do a hypothesis test for little p by using a sample p hat. But for means, we're trying to find a confidence interval or do a hypothesis test for mu, a population mean, given a sample mean x bar. So this example we're going to look at is something called SNAP benefits in the States, and it stands for Supplemental Nutrition Assistance Program. And it is basically a benefit for those who can't afford groceries on their own. They can qualify for these SNAP benefits. Okay? And you can see this is everything that is contained in a SNAP benefit. So in 2020, the maximum monthly SNAP allotment for a household for one person who could not earn income was $194. Right? So what someone decided to do is they took a simple random sample of 31 US grocery stores and found the average cost of the essentials up here. And they got the average cost of the essentials as $199.45, slightly higher than what the SNAP benefit allows, $194. And then you're also told the sample standard deviation. So is there convincing statistical evidence that the maximum SNAP individually monthly allotment, $194, doesn't cover the actual mean price, which we got from that sample that we did? Or did we just get that sample that was slightly higher, $5, $6 higher, by chance alone? So how can we tell if we're asked to do a hypothesis test? What do you see in the question? What phrase do you see? I heard something. Convincing statistical evidence. Exactly. So we want to set up a hypothesis test. And remember, to set up a hypothesis test, the first part is to determine what our null hypothesis is, and then put that in proper math notation, and then what our alternative hypothesis is, put that in, and then define what the true mean is we're testing against. So the null hypothesis, no change. The monthly or the average SNAP benefits is, the true mean is 194. But our sample suggested otherwise, so that's what we want to test. That's the alternative hypothesis. Is it greater than 194? Where mu is the true mean price of an essentials bundle. Okay. Once again, we can do it sort of the long way by hand, as I say, quote unquote. And then there's a special function on our graphing calculator that does it for us quickly, that does all the work that we would do it the long way. So we're just going to look at the long way first, just so you have an idea of what we're doing. Okay. So what we want to find, remember, when we're doing a hypothesis test, doesn't matter whether it's a proportion or a mean. We're trying to find that p-value, which is what's the probability of our sample result, and depending on the question, or greater or less. In this case, it's or greater. Okay, so we're basically trying to determine here what's the probability that the sample was $199.45 or greater. If that probability is very small, that means it's unusual, which suggests there is convincing evidence for the alternative hypothesis. If that probability is high, that means it's not unusual. That means that we got it by chance alone. That means that the null hypothesis holds. We don't reject it. Okay? So in order to set this up, remember when we did probabilities and we used a distribution? Well, for proportions, we used a normal distribution. But remember, for means now, we learned a different distribution, slightly different, a t-distribution, which looks like a normal, but it's usually wider, depending on the degrees of freedom. And the degrees of freedom is always the sample size minus 1. Okay? If there's a high degrees of freedom, the t-distribution looks very close to a normal. If there's a low degrees of freedom, the t-distribution is a little bit wider. It still takes a normal shape, but it's wider than the normal. Okay, so in order to find the p-value, we need to establish that, yes, we can use a t-distribution. We need to establish the mean if we took several samples. And we need to establish the standard error of all these samples that we took. So if we took many, many samples, what's the probability of getting $199.45 or greater? So here, well, the average of our sample means is going to be the same as the null hypothesis mean. Okay? Because that's sort of the mean that we're comparing against. The standard error of the sampling distribution of the means is going to be the standard deviation of the sample, which we were given on the previous page as 25.98, divided by the square root of the sample size, which was square root of, I think, 31. Sample 31 goes through steps. So, the average of our sample means, if we took several, is going to be the null mean, 194. When we calculate this, okay, remember this is, I'll just, make sure I get the right one. Oh no, I've got it here. So if we calculated this, we would get approximately 4.67. So if we assume the null is true, this is what our graph is going to look like of our sampling distribution of means. Okay, we took a whole bunch of sample means. Under the null, they should average out to 194 with a standard error of 4.67. So 4.6, yeah. Anyway. So we need to figure out, okay, how far away, how many standard deviations are we away from the mean? And then we got to find the then we got to find that area, which will give us the probability. So to find the number of standard deviations, remember when we did proportions, we did z-scores. The number of standard deviations is always the data value minus the mean divided the standard deviation. We learned this back to you. But instead of a z-test statistic, which we do for proportions, we're going to do a t-test because we're dealing with a t-distribution, which represents how many standard errors a sample mean, one of these, on average, is away from the null mean, 194. So that means we're going to use this. So to find the t-test statistic, we are going to take our sample mean, our data value, minus the null mean, 194, divided by the standard deviation, which we calculated, or standard error, pardon me, which we calculated above is 4.67. And when you calculate that, you're going to get approximately 1.17 standard errors. So if you think about it, we've got our t-distribution. But this is 194. Okay. Here's like one standard error away, two standard errors away, three standard errors away. We got 1.17. Okay. So we're going to be looking somewhere around here, which looks like a pretty big area. So before I even calculate this area, I'm thinking, yeah, probability is pretty high that I'll get that. Well, let's see if it actually is. How do we find this area? Well, how did we find it using a normal distribution? Normal CDF. How do we find it using a t-distribution? T-CDF, which is on your calculator, graphing calculator. So to get the p-value, which is the probability of your sample, we're going to do t-CDF. And then when you go to that function on your calculator, remember that's not under tests, that's under distribution. So you got to go second vars, and number 5 you'll see, or sorry, number 6 you'll see t-CDF. And it asks for the same thing, except for the mean and standard deviation. It asks for the degrees of freedom. So what's the lower boundary? Well, the lower boundary is 1.17. Sorry, this is actually, because we standardized it, this is actually 0, and this is actually 1. So the lower boundary is 1.17, because we're that many standard deviations away. We're trying to find the area to the right, so our upper is going to be a ridiculously large number, 1,000. And our degrees of freedom, remember, degrees of freedom, sample size minus 1. Our sample size was 31, so our degrees of freedom is 30. So 1.17 for the lower, 1,000 for the upper, degrees of freedom is 30. And we should get approximately 0.126, or 12.6%. Now remember, we usually have a significance level of 0.05. If it's not stated in the question, if it's not stated in the question, assume that's the alpha level. Okay. Well, the probability of getting our sample of $199.45 or bigger is 12.6%. Not unusual. Well above the 5% alpha level. So basically, we would say, because our p-value I'll write it in decimal, 0.126, is above our assumed alpha value, or significance level. Of 0.05, it's not unusual. That means that we fail to reject HO because it's not unusual. So we fail to reject HO. Which means we don't have convincing evidence. Then I just rephrased the question. The maximum SNAP benefit is greater than $194. Because there was a good chance we got our sample mean by chance. So that would be the long one. I mean, you're still using a graphing calculator. But for proportions, for when hypothesis tests, you use normal CDF. For hypothesis test for means, you do TCDF. But again, there's a quicker way where our graphing calculator will do all of this for us from the top here. It will do all of this for us. So let's revisit the question and do the four-step process. Okay? And again, so it does say here, alpha equals 0.05. So state the hypothesis test. We want to state the null and the alternative. The null, the true average is 194. What we're testing is it actually bigger than or larger than 194. Where mu is true mean price of SNAP benefits. Plan. Well, with confidence intervals we construct, with hypothesis tests we perform or conduct. So we are going to perform a one sample t-test. Because remember, with means we use t for the true mean. If the three conditions are met. So random. 10%. And remember, with means, we do large sample, greater than or equal to 30. So this is going back to the first page. Says SRS of 31 US grocery stores. So grocery stores were randomly selected. We're good. 10% is the number of grocery stores, 31. Less than 10% of all grocery stores in the US? Absolutely. And the large sample, which allows us to use a t-distribution, well, is the sample size greater than or equal to 30? Yes. So that means that we can go ahead and use a certain function on our graphing calculator, which is t-test. Don't look for one sample t-test, just t-test. So now you go to your graphing calculator. Go to stat because we want to go to tests. Number 2 is the t-test. Now, first thing it says is input. Make sure stats is highlighted because stats allows you to enter the results or enter the values we need. If you go to data and hit enter, it's going to ask for a list, which is what we don't do. So you want to make sure you're on stats. So we are doing a test. T-test. The assumed mean is 194. The sample mean X bar is 199.45. The standard deviation was given on the first page at the beginning of the question, 2598. The sample size is 31. And we are looking for mu greater than the null, greater than 194. You always want to make sure you get that one right, or you're going to get a different value. So the sample standard deviation was 25.98. Sample size 31. We are greater than. And then when you calculate that, you're going to get several values. You want to look for little p, 0.126. That's our p value. Which is what we got when we did it the long way. And then conclude just exactly what we did on the previous page. That's our p-value. It's less than our alpha value. Greater, sorry, thank you. Fail to reject. HO. Don't have convincing evidence. staff benefits. Are greater. Than $194. And so for our purposes, this is the one you want to focus on. Don't worry so much about the previous page. The previous page just sort of shows you the why of why we can do this. The longhand. Okay. Okay.